We've been studying rational functions in the form f of x is equal to g of x over h of x, where g of x and h of x are both polynomial functions. We started out by looking at the simple reciprocal function, which was that f of x is equal to some constant over x. Well, the numerator of this type of function is a constant, so it has a degree of 0. The denominator is a linear because it's got a degree of 1, and what we saw was that we get a horizontal asymptote at y equals 0, which is the x-axis, and a vertical asymptote at x equals 0, which is the y-axis. Then we saw that we could transform these equations by doing translations, and that when we did and then simplified them, we ended up with a function in the form ax plus b over cx plus d, which is still a polynomial function, but it has linear equations on top and bottom. We saw that our horizontal asymptote in this case then becomes y equals the ratio of a to c, and our vertical asymptote changes also. It becomes x equals the ratio of negative d over c, which is the point that makes cx plus d equal to 0, or makes the equation undefined. Well, we learned pretty in-depth about this, how to graph them, how to find points on those graphs, make some nice accurate graphs. And that's where your book leaves off. I want to extend this a little bit. We're not going to go as nearly as in-depth in the new types of problems that we're going to work, but I do at least want you to be able to draw a rough graph or rough sketch of the graph and put in the asymptotes and maybe even the x and y intercepts, but you won't have as many accurate points until we get more tools under our belt when we start studying calculus. But for right now, I want you to look at a few more types of rational functions. One type I want you to look at is a function where I've got a linear equation on top, but I have a quadratic equation on bottom. So whenever I have this situation, once again I'm going to notice the degree of my polynomial functions. The top numerator is a degree of 1, since that's a linear function, and the denominator has a degree of 2, which is a quadratic function. Well, just like the original reciprocal function, anytime that degree of the numerator is less than the denominator, you're going to have a horizontal asymptote at y equals 0, or the x-axis. That will always hold true when those degree of the numerator is less than the degree of the denominator. Now, as far as my vertical asymptotes, what we did was found where the denominator was equal to 0, so let's do that again. X minus 4 equals 0. I can do that in a couple of ways, but I think I'll factor this one since it's a difference of square. It makes it very easy to do so. So x could be negative 2 or x could be 2. Both of those would make the denominator of that fraction 0 and therefore would be undefined. So does that mean that I have two asymptotes? Well, let's look at the graph. If I put that into my calculator and graph it, it comes up, it looks like I've got one at x equal 2, but something else is going on at negative 2. I don't have another asymptote. So I'm going to zoom in. I'll look at the decimal screen. I see over here at negative 2 there seems to be a gap. We call that a hole in the graph. And so whenever you've got a quadratic in the denominator or a degree higher than 1, then whatever makes that function undefined doesn't necessarily give you an asymptote. It may give you a hole in the graph. So how can you tell your asymptote from a hole in the graph? Well, the way that you do it is plug in. So f of 2, if I plug in 2, I get 2 plus 2 is 4 over 2 squared minus 4, which is 0. And 4 over 0 is undefined. And so I have a vertical asymptote at x equals 2. Well, let's see what happened at f of negative 2, because obviously it was not a asymptote, it was a hole in the graph. When I plug in negative 2, what I end up with is 0 over 0, which though technically you can't have a 0 on the bottom, and it would be undefined. When you have 0 over 0, we call that indeterminate form. And what an indeterminate form tells you is that you have a hole in the graph. Now, why does one come out to be a hole in the graph and the other a vertical asymptote? Well, if you think in terms of taking our original equation, f of x is equal to x plus 2, and factor that bottom, x plus 2, or the denominator, x minus 2, we can see that the x plus 2's will cancel out. And what I get is an equivalent equation, 1 over x minus 2. And those two graphs, f of x equals 1 over x minus 2, and f of x equal x plus 2 over x squared minus 4, will be identical everywhere except that one point. And that one point is where f is negative 2. It's indeterminate, and that means it's a hole in the graph. Now, let's look at another one similar to that. Here I see that the degree of the numerator is less than the denominator, so I'm going to have a horizontal asymptote, once again at y equals 0. When I find my points that make the denominator equal to 0, x could be equal to either positive or negative 2. When I plug in this case, though, f of 2 is 5 over 0, and f of negative 2 becomes 1 over 0, so I have two vertical asymptotes, x equals 2 and x equals negative 2. I would like for you to look at that graph, though, just to show you one thing that you may not be aware of, and that is that when I change this to a 3 here and then graph it, notice we do get our 2, but it looks to me like this is actually crossing that x-axis, but that x-axis is an asymptote. How does that happen? Well, what a lot of people don't realize is that when we talk about an asymptote, what we're talking about is end behavior of the graph. What is going on is your value approaches infinity. As the x gets larger and larger and larger, then this is going to get closer and closer to 0. Because of this fraction here, when I've got an x squared on bottom, it's going to grow tremendously more than the top, so it's going to approach 0. When I, however, go toward negative infinity, that's going to be the same. But that doesn't mean that it will never cross. If I were to zoom in, and I'm going to do a box around it, and look at what's happening just over here on this left side, and I'll come down a little bit and then move to the left, and I'm going to box this in so that I can see what's going on. When I look at that graph, I see in fact it does cross. It crosses at x equal negative 3, because that would give me 0 on top without making the bottom undefined. But what I would notice if I kept going further and further toward negative infinity is that line would come back up and approach 0. So don't have the misconception that it will never cross an asymptote. It can. It just won't be crossing it or touching it again out towards the ends of the graph or the end behavior. Let's look at what happens when I have a quadratic over a quadratic. Well, just as when I had a linear over a linear, my horizontal asymptote is going to be y equals the ratio of the lead coefficients, or in this case, y equals 2 over 1 or 2. For my x-axis, for my vertical asymptote, I know that it could be positive or negative 2. If I plug in positive 2, that obviously won't be 0 on top. And if I plug in negative 2, I'm going to get 4 minus 14. No, that 2 squared will be 4. 4 times 2 is 8 minus 14, which is going to be a negative 6, plus 12 is still going to be a positive number. So I have 2 vertical asymptotes there. 1 horizontal, 2 vertical. If I were to look at that graph, I would see that what I end up with is, once again, it actually does cross that asymptote of y equal 2 in the inside, but out toward the ends of it, it would approach y equals 2 on both the positive, as it approaches both positive and negative infinity. I want to look at one more situation, and that is where when the numerator is bigger than the denominator. Once again, I can check for my vertical asymptotes. My vertical asymptotes are going to be x equal positive or negative 2. If I were to plug those in, I would get a number over 0 for both of them. When that denominator is bigger than the numerator, however, you do not get a horizontal asymptote. What you get is called a slant asymptote. And the way that we find the slant asymptote, which is just a line that it will approach as x approaches infinity and negative infinity in behavior of the graph, but it will not be a horizontal or vertical line, but will be a slanted line, which is why it's called a slant asymptote. The way to find it is the way that we transformed our linear over linear back into a reciprocal function, and that was to use polynomial long division. We're going to do that again here. X squared goes into x cubed x times. When I multiply, I get x squared, or excuse me, x cubed. I don't have an x squared term, so I'm going to put in 0x squared just to fill it, and x minus 4 is negative 4x. And so I get x squared plus 8x. When I subtract, x squared goes into x squared one time. I get x squared. I have no x's, and then minus 4. So when I subtract, I get 8x plus 5. X squared doesn't go in that, so I have a remainder of 8x plus 5 over x squared minus 4. Now, when we're looking at our slant asymptote, we can ignore the remainder, and our slant asymptote is going to be the line y equals x plus 1. That is a slant asymptote. So let's see what that would look like on the graph. I hope I have time to get this in there for you. We're going to have x cubed plus x squared plus 4x plus 1, close that, divided by x squared minus 4. And when I graph this, I'm going to do a zoom 6 back to my regular window. Notice this is what the graph looks like. It's got 3 parts. It's got what looks like could be somewhat similar to a hyperbola with a cubic function in the middle. But here's what I want you to notice. If I go in there and add n into the y2, the y equals x plus 1, and graph both of those together, you can see our line that goes through there that both ends approach as it approaches infinity. So we have an asymptote, but that is a slanted asymptote. Now, what do I expect you to know out of this lesson? Actually, all I want you to do, I wouldn't even expect you to be able to draw the graph of that one right now. Now, we're going to learn how to do that a little bit later on in this course, but for right now, I just want you to be able to find your asymptotes. If it is like a simple one, I may want you to find the x and y intercepts, but in something this complicated, I wouldn't even ask you to do that. I would just ask you for your asymptotes on this.